I sometimes begin with a simple question, one that looks almost too small to matter. If all you have is a straight stick and an open patch of ground, how much of the universe could you actually understand? It sounds like a riddle or perhaps a trick from a forgotten science class. Yet whenever I ask it even to seasoned astronomers, there's a brief pause, a sense that something ordinary might hide something profound. I remember standing beside an old sundial in a quiet museum courtyard. People pass by without slowing their eyes on their phones, unaware that the thin shadow sliding across the stone beneath them once carried the weight of entire civilizations. I realized in that moment that before telescopes, before clocks, before mathematics became a discipline of symbols and abstraction, the human relationship with the cosmos rested on nothing more than careful noticing. Tonight, I want to take you back to that form of noticing, patient, quiet, almost meditative, in its simplicity, yet entirely grounded in verifiable science. Because with nothing but a stick in the ground, you can discover that the Earth spins. So as you settle in, breathe easily, and let your attention soften, I invite you into a slow journey. A journey where each observation gathers weight, and each shadow carries meaning. And it all begins with a single question: what happens when the sun meets a stick you place in the ground when I place a stick upright in the ground? The scene doesn't look like science. It looks like the beginning of nothing, in particular a slender line of wood, a patch of soil, and sunlight drifting across the sky. And yet from this simple arrangement, one of the oldest and most reliable truths about our world quietly emerges. To reach it, all I have to do is watch the shadow. You might think you already know what that shadow will do. It will stretch long in the morning, shrink toward midday, and lengthen again as the sun descends. This feels obvious because you've lived inside this rhythm your entire life. But when you watch it deliberately, when you tune your attention to its slow choreography, the experience changes. The shortening of the shadow is not merely a visual fact. It becomes a measurement, a clock, a quiet signature of Earth's geometry and motion. If I focus on the shadow's retreat, I notice something precise. It doesn't shorten endlessly. It tightens its arc until for just a brief moment it reaches the smallest length it will have all day. This moment marks what ancient observers wisely called the true midday, long before we invented time zones or mechanical clocks. Today we call it local noon. Local noon is not the noon displayed on your watch unless you happen to live at the center of your time zone and it happens to be a day when the sun's apparent motion aligns closely with the clock. Most of the time, the sun and the clock disagree, but the stick never does. It follows the sun alone, independent of human schedules. When the shadow reaches this minimum length, something else remarkable happens. It aligns perfectly with one of the cardinal directions. If I stand north of Earth's equator, the shadow at true midday points directly toward the north. If I stand south of the equator, it points directly toward the south. This is not a guess or an approximation. It is a consequence of the geometry between you, the stick, and the sunday. So in the span of a single day, without a compass, without a phone, without even a written record, I can determine the precise moment of midday and the location of the north-south line. This is the backbone of navigation. Entire civilizations oriented their temples, their streets, and their calendars from this simple observation. As I watch the shadow extend again in the afternoon, I'm reminded that none of this depends on the stick itself. Its length does not matter. Its material does not matter. What matters is that it is straight and that you take the time to watch what it reveals. When people first learn that the Earth rotates, the idea tends to feel abstract. You can't feel the rotation. You can't hear it or sense it in any direct way. Yet the shrinking and lengthening of this shadow is the observable artifact of that spin. You are watching sunlight shift across your landscape because Earth turns beneath it. And while this daily cycle is familiar, there's an aspect of it that often goes unnoticed. Between the moment the shadow begins to shorten after sunrise and the moment it lengthens again towards sunset, the sun has traced a smooth, continuous path across the sky. But the high point of that path, the moment when the sun reaches its greatest altitude, is not chosen by culture or technology. It is chosen by physics. Gravity holds Earth in place. Earth's rotation carries you in and out of the sun's illumination. The geometry determines when that illumination is most direct. If you were to stand by your stick long enough, with the patience of someone observing nature at its slowest scales, you would start to understand that this apparently simple movement contains a world of meaning. You would see, for example, that the sun never takes the same path across the sky 2 days in a row. The midday shadow might be shorter or longer than yesterday's. The exact moment of local noon might shift slightly. These tiny variations are fingerprints of deeper motions. Earth's orbit around the sun, the tilt of its axis. The fact that the year is not a perfect sequence of identical days, but a gradual unfolding of celestial mechanics. But right now in this first chapter of our journey, I want to stay grounded literally. I want you to imagine yourself sitting near that stick, quietly aware of the sun's slow ascent. You might feel the ground warm beneath you. You might notice the sharpness of the shadow soften as clouds drift by. None of this interrupts the fundamental truth. The shadow will still reach its minimum even if you step away for a while, even if you forget about it and return later. The Earth's rotation is steady enough that these rhythms hold across continents, seasons, and centuries. NASA's modern solar observations confirm this regularity with exquisite precision. Satellites monitor the sun's position relative to Earth with instruments far more capable than any ancient observer could imagine. And yet, despite this technological advancement, the basic pattern remains exactly what your stick reveals. The sun appears to rise because Earth rotates. It reaches a peak altitude based on your latitude. It casts a shadow whose length is governed by the same geometry that satellites now measure from orbit. There's something deeply grounding in that continuity. When I stand beside a simple stick in the soil, I'm not reenacting a primitive version of astronomy. I'm connecting to the same physical truths that guide space agencies as they steer probes to other planets. The sophistication of their equipment does not replace the stick. It merely refines what the stick already implies. I often think of how much information is hidden in plain sight, how many scientific principles are acting around us quietly without our awareness. If you walk through a city at midday, you might never consider that every shadow touches the north-south direction, that the length of every vertical pole's shadow is a direct measurement of Earth's tilt on that date. These facts persist whether you pay attention or not. And this is where this simple observation becomes something more meaningful. When you and I watch that shadow shorten, we're not learning something new about the world. We're noticing something that was always there. In that act of noticing something shifts, the day becomes more than a background process. It becomes a vast mechanism unfolding with quiet regularity. A quiet morning often begins with the expectation that the sun will appear from a familiar place on the horizon. Many people grow up hearing the phrase, "The sun rises in the east and sets in the west," spoken with the confidence reserved for absolute truths. Yet the horizon patient and vast tells a more subtle story. A single stick in the ground becomes a witness to that story long before clocks, compasses, or modern navigation existed. A careful observer revisiting the same spot day after day discovers that the sunrise refuses to stay anchored to a single point. It drifts northward for weeks, pauses briefly, then drifts southward. This slow migration is invisible in the rush of ordinary life, but becomes unmistakable once attention is directed toward it. Long before modern astronomy, ancient cultures from Egypt to Mesoamerica relied on this drifting sunrise to organize their calendars, harvest cycles, and ceremonies. During my own early encounters with this phenomenon, the realization felt strangely destabilizing. The eastern horizon had always seemed like a fixed border where day breaks. Learning that the sun only rises exactly due east on 2 days, each year the equinoxes reshaped that intuition. Those equinox mornings are special not because something dramatic happens in the sky, but because nothing extra happens. The sun climbs from the midpoint of its journey along the horizon, dividing day and night into equal halves. The Latin roots of the word equinox, meaning equal night, capture that balance. Solstices reveal another layer of the sun's choreography. At the height of summer in the northern hemisphere, the sunrise reaches its farthest point, north of east. That point marks the longest arc the sun will trace across the sky, leading to the year's shortest midday shadow and the most generous span of daylight. Winter solstice offers the opposite. The sun emerges from its southernmost position, travels low across the sky, and produces the longest noontime shadow. These extremes define the turning points of the seasons, each one mapped effortlessly by nothing more than a stick and patient observation. Accounts from NASA's solar dynamics missions highlight this same shifting geometry with remarkable detail. Space-based instruments reveal the precise tilt of Earth's axis, about 23.5 degrees, and demonstrate how that tilt governs the sun's changing position throughout the year. While satellites quantify the angles with extraordinary accuracy, the essential insight remains accessible even to someone living thousands of years before the invention of orbiting observatories. Individuals who rely on mechanical clocks or digital devices tend to overlook how fluid the sun's path truly is. The calendar keeps time for society, but the horizon keeps time for the planet. By revisiting the stick's shadow and watching the sunrise creep along the horizon, one begins to sense Earth as a moving world, not a static platform suspended beneath a predictable sky. This awareness builds slowly, but its impact can be profound. A person standing outdoors becomes part of a cosmic rhythm rather than a mere spectator. Ancient architects knew this rhythm intimately. Structures such as the Karnak Temple in Egypt or the Mayan Observatory at Chichen Itza align with specific points of the solar year, often capturing sunrise or sunset light in carefully orchestrated way. Their builders did not possess advanced mathematics or telescopes. They relied on repeated observation, the slow accumulation of knowledge, and a deep familiarity with the local sky. Modern researchers from institutions like Cambridge and the University of Arizona continue to examine these alignments, confirming that many ancient claims about solar geometry hold up under rigorous analysis. The returning drift of sunrise also highlights something subtle about human perception. People living indoors, surrounded by artificial lighting, rarely notice gradual shifts in natural patterns. A civilization living in close contact with the land would interpret those shifts as signals, guides for agriculture, markers for ritual or boundaries between seasons. Today's technology-rich world often masks the very cues that shaped humanity's early relationship with nature. Over the years, while studying planetary dynamics, I found this particular phenomenon, sunrise migration, to be one of the most striking pieces of evidence that Earth is not simply rotating, but also orbiting. The angle at which sunlight arrives changes because our planet leans while circling the Sunday. This combination of tilt and orbit creates the continually changing sunrise point. In essence, the horizon acts like a massive calendar, updating itself slowly and reliably. It becomes clear that the simplistic adage about east and west survives mostly because people seldom look closely. The sun does rise in the general eastern half of the sky, but that is where the accuracy ends. It occupies a range, not a fixed point, and that range encodes essential truths about Earth's motion. For a civilization that once tracked seasons to avoid famine, this understanding meant survival. For a person today, it offers a quiet way to reconnect with the pace of natural cycles. Consider a calm morning spent near the stick. The air may feel cool, the world unhurried. The shadow of the stick stretches behind it, pointing toward a place where the sun has not yet appeared. On some days, the shadow aligns slightly differently than the week before. This delicate shift becomes the earliest sign of a changing season, not a date printed on a calendar, but a geometric reality unfolding in real time. By the time the sun has taken its place in the sky, the stick has already captured data. That data does not require interpretation by complex instruments. A notebook, a memory, or even a simple stone placed at the point where sunrise first appeared can record the trend. Over many mornings, a pattern emerges. The horizon becomes a grand diagram, and the stick becomes a pointer tracing its annual curve. Precise timekeeping began long before mechanical clocks appeared. The daily motion of the sun offers one kind of measurement familiar to every society that relied on agriculture or navigation. Yet a different measurement reveals itself once attention shifts from the sun to the distant stars. The contrast between these two cycles exposes a structural feature of Earth's motion, one that cannot be detected from sunlight alone. A solar day is defined by the interval between two consecutive moments when the sun reaches its highest point in the sky. Most people recognize this as noon to noon. The duration averages 24 hours over the course of a year. The emphasis here is on averages because Earth's elliptical orbit and axial tilt cause the real solar day to vary slightly. Those variations are smoothed out in civil timekeeping, but they remain measurable with consistent observation near a fixed stick in the ground. A sidereal day relies on a different reference frame. Instead of tracking the sun, the measurement uses a distant star, a point so far away that its apparent position provides a stable backdrop. When the same star crosses the same reference line in the sky on 2 consecutive nights, the interval is about 23 hours, 56 minutes, and a few extra seconds. This difference of roughly 4 minutes may appear trivial from a human point of view. In astronomy, it signals a fundamental truth: Earth must complete slightly more than one full rotation relative to the stars in order to bring the sun back to the same noontime position. Earth rotates once with respect to distant stars, but during that rotation, it also moves along its orbit around the Sunday. The planet advances a small fraction of its orbital path every day. To realign the sun with the same meridian Earth must rotate a little farther. The additional rotation requires about 4 minutes. This relationship, widely documented by institutions such as NASA's Goddard Space Flight Center and the Royal Astronomical Society, confirms that Earth orbits the sun rather than the opposite. A stick and a fixed observing position allow both cycles to be detected without specialized tools. At solar noon, the shadow cast by the stick reaches its minimum. At night, that same stick can be used to define a simple line of sight, aligning the tip of the gnomon with a chosen star. Tracking the moment when the star returns to that exact alignment yields the sidereal interval. Ancient astronomers in Greece, Babylon, and China used methods very similar to this, often employing architectural structures rather than portable sticks, but the underlying principle remains identical. The 4-minute discrepancy accumulates over time. After 1 month, the stars appear to rise roughly 2 hours earlier than the Sunday. After 6 months, nighttime viewing reveals an entirely different set of constellations from those visible half a year before. Satellites operated by the European Space Agency, such as Gaia, now chart stellar positions with extraordinary precision. But the large-scale effect, the shifting backdrop of constellations, was recognized thousands of years before such mission existed. This gradual displacement of the stars is what gives rise to the familiar idea of the zodiac. Ancient skywatchers observed that the sun appeared each month against a different group of distant stars. The sun itself does not physically move among the stars. Instead, Earth's orbital motion causes the sun to seem to migrate across the sky. The concept of signs emerged from this apparent motion. Contemporary astronomy, supported by measurements from observatories across the world, treats this as a geometric consequence of Earth's orbit, not as a mechanism influencing human behavior. It is worth noting that solar and sidereal days also differ on other planets. Mars, for example, has a solar day only slightly longer than Earth's roughly 24 hours and 40 minutes, while its sidereal day is about 24 hours and 37 minutes. The difference once again reflects the same principal rotation combined with orbital motion. NASA's Mars landers calibrate their internal clocks according to the Martian solar day because engineering operations depend on local sunlight. Meanwhile, astronomical tracking uses the sidereal reference frame. Returning to Earth, the simple act of measuring both kinds of days reveals that humans inhabit a world in motion through a larger space. The sun's behavior defines the cycle of life on the surface light temperature biological rhythms. The stars define the planet's broader relationship to space itself, mapping out its position within the Milky Way. Observing both cycles brings these two scales of motion into a single frame of understanding. Civil timekeeping eventually adopted the solar day as its standard because daily life responds to sunlight. Clocks, time zones, and coordinated universal time (UTC) all maintain this solar framework. Scientists, on the other hand, frequently work in sidereal units when pointing telescopes, tracking satellites, or aligning instruments with deep sky targets. The coexistence of these two systems illustrates how different scientific questions can require different definitions of something as seemingly straightforward as a day. Extended observation of both cycles also reveals a long-term pattern. Earth's rotation is slowly decreasing in speed. Tidal interactions with the moon transfer angular momentum away from Earth, causing days to grow very slightly longer over geological time. Evidence for this can be found in ancient coral fossils, whose growth rings suggest that hundreds of millions of years ago, a year contained more days than it does today. Modern measurements from lunar laser ranging experiments conducted by NASA and several university research teams confirm that the moon gradually drifts away from Earth, altering the dynamics of the system. All of this becomes accessible through the patient use of a simple stick. The stick does not detect the rotation slowing, it does not reveal geological timescales. What it does provide is the foundation, the ability to distinguish between the sun's cycle and the cycle of the stars. Everything else builds on that distinction. Observing the difference calls for nothing more than clarity of attention. A midday shadow marks the solar cycle. A nightly alignment marks the sidereal one. Combined, these measurements disclose Earth's dual motion spinning on its axis while orbiting the Sunday. The insight is not philosophical or symbolic, it is geometric, and it emerges naturally from the sky above every person on Earth. Precise timekeeping began long before mechanical clocks appeared. The daily motion of the sun offers one kind of measurement familiar to every society that relied on agriculture or navigation. Yet a different measurement reveals itself once attention shifts from the sun to the distant stars. The contrast between these two cycles exposes a structural feature of Earth's motion, one that cannot be detected from sunlight alone. A solar day is defined by the interval between two consecutive moments when the sun reaches its highest point in the sky. Most people recognize this as noon to noon. The duration averages 24 hours over the course of a year. The emphasis here is on averages because Earth's elliptical orbit and axial tilt cause the real solar day to vary slightly. Those variations are smoothed out in civil timekeeping, but they remain measurable with consistent observation near a fixed stick in the ground. A sidereal day relies on a different reference frame. Instead of tracking the sun, the measurement uses a distant star, a point so far away that its apparent position provides a stable backdrop. When the same star crosses the same reference line in the sky on 2 consecutive nights, the interval is about 23 hours, 56 minutes, and a few extra seconds. This difference of roughly 4 minutes may appear trivial from a human point of view. In astronomy, it signals a fundamental truth. Earth must complete slightly more than one full rotation relative to the stars in order to bring the sun back to the same noontime position. Earth rotates once with respect to distant stars, but during that rotation it also moves along its orbit around the Sunday. The planet advances a small fraction of its orbital path every day. To realign the sun with the same meridian, Earth must rotate a little farther. The additional rotation requires about 4 minutes. This relationship, widely documented by institutions such as NASA's Goddard Space Flight Center and the Royal Astronomical Society, confirms that Earth orbits the sun rather than the opposite. A stick and a fixed observing position allow both cycles to be detected without specialized tools. At solar noon, the shadow cast by the stick reaches its minimum. At night, that same stick can be used to define a simple line of sight, aligning the tip of the gnomon with a chosen star. Tracking the moment when the star returns to that exact alignment yields the sidereal interval. Ancient astronomers in Greece, Babylon, and China used methods very similar to this, often employing architectural structures rather than portable sticks, but the underlying principle remains identical. The 4-minute discrepancy accumulates over time. After 1 month, the stars appear to rise roughly 2 hours earlier than the Sunday. After 6 months, nighttime viewing reveals an entirely different set of constellations from those visible half a year before. Satellites operated by the European Space Agency, such as Gaia, now chart stellar positions with extraordinary precision. But the large-scale effect, the shifting backdrop of constellations, was recognized thousands of years before such missions existed. This gradual displacement of the stars is what gives rise to the familiar idea of the zodiac. Ancient skywatchers observed that the sun appeared each month against a different group of distant stars. The sun itself does not physically move among the stars. Instead, Earth's orbital motion causes the sun to seem to migrate across the sky. The concept of signs emerged from this apparent motion. Contemporary astronomy, supported by measurements from observatories across the world, treats this as a geometric consequence of Earth's orbit, not as a mechanism influencing human behavior. It is worth noting that solar and sidereal days also differ on other planets. Mars, for example, has a solar day only slightly longer than Earth's roughly 24 hours and 40 minutes, while its sidereal day is about 24 hours and 37 minutes. The difference, once again, reflects the same principle, rotation, combined with orbital motion. NASA's Mars landers calibrate their internal clocks according to the Martian solar day, because engineering operations depend on local sunlight. Meanwhile, astronomical tracking uses the sidereal reference frame. Returning to Earth, the simple act of measuring both kinds of days reveals that humans inhabit a world in motion through a larger space. The sun's behavior defines the cycle of life on the surface light temperature biological rhythms. The stars define the planet's broader relationship to space itself, mapping out its position within the Milky Way. Observing both cycles brings these two scales of motion into a single frame of understanding. Civil timekeeping eventually adopted the solar day as its standard because daily life responds to sunlight. Clocks, time zones, and coordinated universal time UTC all maintain this solar framework. Scientists, on the other hand, frequently work in sidereal units when pointing telescopes, tracking satellites, or aligning instruments with deep sky targets. The coexistence of these two systems illustrates how different scientific questions can require different definitions of something as seemingly straightforward as a day. Extended observation of both cycles also reveals a long-term pattern. Earth's rotation is slowly decreasing in speed. Tidal interactions with the moon transfer angular momentum away from Earth, causing days to grow very slightly longer over geological time. Evidence for this can be found in ancient coral fossils, whose growth rings suggest that hundreds of millions of years ago, a year contained more days than it does today. Modern measurements from lunar laser ranging experiments conducted by NASA and several university research teams confirm that the moon gradually drifts away from Earth, altering the dynamics of the system. All of this becomes accessible through the patient use of a simple stick. The stick does not detect the rotation slowing. It does not reveal geological timescales. What it does provide is the foundation, the ability to distinguish between the sun's cycle and the cycle of the stars. Everything else builds on that distinction. Observing the difference calls for nothing more than clarity of attention. A midday shadow marks the solar cycle. A nightly alignment marks the sidereal one. Combined, these measurements disclose Earth's dual motion spinning on its axis while orbiting the Sunday. The insight is not philosophical or symbolic, it is geometric, and it emerges naturally from the sky above every person on Earth. A year of marking the stick's noontime shadow produces a record quite different from the clean symmetry. Many people imagine the expectation might be that the shortest shadow of each day would fall along a tidy north-south line, repeating precisely from one noon to the next. Reality offers something far more intricate. Over the span of 12 months, the points plotted at clock noon form a long looping pattern in the soil, a narrow waist in the center, two large lobes above and below, The resulting shape resembles a tilted figure 8. Astronomers call it the analemma. This pattern, familiar to anyone who has studied sundials or examined detailed globes, emerges from two independent features of Earth's motion. The first is the tilt of Earth's axis, approximately 23.5 degrees relative to the plane of the planet's orbit. The second is the eccentricity or slight elliptical nature of that orbit. Each effect modifies the sun's apparent position in the sky. Combined, they generate a path that cannot be explained by a single factor alone. Earth's axial tilt determines the height of the sun at noon across the seasons. A higher sun in summer yields a shorter midday shadow. A lower sun in winter creates a longer one. This vertical variation is responsible for the elongated shape of the analemma, its top and bottom sections. The orbit's eccentricity adds the horizontal displacement. Solar time does not progress at a perfectly uniform rate because Earth moves slightly faster when nearer the sun and slightly slower when farther away. This fact was quantified centuries ago by Johannes Kepler, whose work on planetary motion laid the foundation for orbital mechanics still used in modern spaceflight. Observatories today, including the Solar Dynamics Observatory operated by NASA, confirm these principles with continuous measurements of solar position relative to Earth's frame of reference. Instruments detect the annual oscillation in the sun's apparent longitude caused by varying orbital speed and its oscillation in declination caused by axial tilt. The analemma is essentially a graph of both effects plotted together against clock time. A stick in the ground demonstrates this graph beautifully. By placing a mark at the tip of the stick's shadow every day at exactly the same clock time noon by a modern watch, the plot reveals the discrepancy between clock noon and sun noon. On some days, the sun reaches its highest point earlier than the clock indicates. On other days, it arrives late. The difference can reach roughly 15 minutes in either direction, depending on the time of year. This variation is known as the equation of time. Certain dates bring the two time systems into temporary agreement. The sun crosses the meridian at almost exactly clock noon on 4 occasions: in mid-April, mid-June, early September, and late December. These dates do not coincide with solstices or equinoxes. They arise strictly from the interaction of orbital speed and axial tilt. A sundial carved with an analemma allows the user to compensate for these seasonal offsets, providing a practical conversion between solar and civil time. The figure 8's asymmetry contains another piece of information. Earth's orbit is not a perfect ellipse with large eccentricity, but it is eccentric enough that the Sun-Earth distance varies by about 3% between closest and farthest approach. This subtle difference is sufficient to distort the analemma's lobes. The lobe corresponding to the northern hemisphere's winter is typically larger because Earth moves faster near perihelion, the point in its orbit closest to the sun, which occurs in early January. The faster orbital speed causes larger time shifts, extending the lower loop of the figure 8. Ancient observers could not derive orbital equations, yet the effects were unmistakable. Some medieval sundials carved into cathedral walls include engraved traces of the analemma, demonstrating that craftsmen recognized the pattern long before its mathematical basis was established. Historical research from institutions such as the British Sundial Society and the University of Vienna has documented numerous examples across Europe and the Middle East, indicating a widespread empirical understanding of the sun's irregular motion. The figure 8 does more than mark a pattern. It encapsulates the architecture of the Earth-Sun system. A person studying the ground over 1 year gains insight into axial tilt orbital shape seasonal timing and the structure of apparent solar motion. None of these concepts require abstract mathematics in their initial form. The experience is observational, almost archaeological, uncovering a shape that records the planet's behavior. In scientific terms, the analemma also serves as evidence that Earth's rotation remains steady across the year. The variations observed in the figure 8 originate entirely from the sun's apparent position, not from changes in the length of the day. High precision measurements from atomic clocks distributed globally under the supervision of the International Bureau of Weights and Measures, confirm that Earth's rotation exhibits only gradual long-term variations, not daily oscillations of the kind that would distort the analemma's form. The consistency of the figure 8 reinforces this stability. Modern analogs of the ancient stick experiment appear in long-exposure astrophotography. Skilled photographers create solar analemma images by taking one picture of the sun at the same time of day over the course of a year, then merging the exposures. The composite reveals the same figure 8 captured by the stick shadow. Observatories across the world, including those supported by the European Southern Observatory, have documented these images as part of public science communication efforts demonstrating the continuity between ancient observation and contemporary technique. Interpreting the analemma introduces a broader perspective on what constitutes a day. A civil day maintains strict uniformity for the sake of schedules and global coordination. Solar time, by contrast, reflects the natural irregularities of Earth's motion. The two coexist in tension, and the analemma sits exactly at that intersection. The stick does not align itself to human conventions. It aligns itself to the Sunday. The discrepancy becomes visible only because a clock provides a competing standard. Patterns obtained from such a simple experiment serve as a reminder that complex astronomical phenomena often emerge from straightforward observations repeated patiently. A stick, a shadow, and a consistent viewing time allow the Earth's orbit and tilt to announce themselves without ambiguity. Two shadows cast in two different cities can reveal the dimensions of an entire planet. That realization stands among the most elegant in the history of science. Long before spacecraft photographed Earth as a sphere, long before satellites mapped its surface, the curvature of the world could be inferred using sunlight geometry and careful coordination. The experiment commonly associated with this discovery took place in the 3rd century BCE during the intellectual peak of Hellenistic Alexandria. Eratosthenes, who served as chief librarian of the Great Library, examined reports from the southern Egyptian city of Syene, now Aswan, where the sun at noon on the summer solstice illuminated the bottom of deep wells. Accounts from that region noted the absence of a noon shadow. The sun appeared directly overhead, a rare occurrence limited to latitudes near the Tropic of Cancer. Alexandria, located several hundred kilometers to the north, did not share that experience. A vertical stick placed there on the same date produced a measurable shadow. The contrast between the two cities set the stage for a remarkable inference. If Earth were flat, both locations would receive sunlight at the same angle, yielding identical shadow lengths. The difference provided the essential clue that the planet must be curved. Eratosthenes measured the shadow in Alexandria and found the angle between the stick and the sun's direction to be roughly equivalent to 1/50th of a full circle. This estimate indicated that the distance from Alexandria to Syene represented about 1/50th of Earth's circumference. Multiplying the distance by 50 produced a figure remarkably close to modern measurements, approximately 40,000 kilometers for the full circumference. The exact value he used for distance was expressed in the unit stadia, whose precise length remains debated among historians. Even with uncertainties, the result falls within 10% of values determined by satellite geodesy today. NASA's Goddard Space Flight Center maintains detailed data on Earth's shape and size derived from laser-ranging satellite altimetry and gravimetric measurements. These techniques reveal Earth as an oblate spheroid, slightly flattened at the poles and wider at the equator. Yet the difference from a perfect sphere is modest enough that Eratosthenes' method remains valid in its original form. A vertical stick correctly measured at 2 latitudes still carries enough information to reproduce the essence of his result. The experiment does not require the cities to be on the same longitude, although the calculation becomes more straightforward when they are. What matters is that the sunlight arrives from such a great distance that its rays can be treated as parallel. In reality, the sun is not infinitely far away. It lies about 150 million kilometers from Earth. The slight divergence of its rays is negligible for the scale of these measurements. Modern solar parallax methods quantify this divergence, but its impact on Eratosthenes' calculation is far smaller than the uncertainties in the unit of stadia. Reproducing the experiment today yields results that align closely with satellite-based measurements. Astronomy educators often coordinate observations between schools, separated by known distances, inviting students to measure shadow angles at local noon. Comparing these contributions reveals Earth's curvature directly without requiring advanced optics or digital instruments. Organizations such as the Astronomical Society of the Pacific have promoted such programs for decades, demonstrating that even in the age of precision geodesy, fundamental observations retain their power. The logic underlying the experiment extends beyond Earth. Planetary scientists use analogous reasoning when studying the sizes of other celestial bodies. Radar ranging from orbiters provides direct measurements for nearby planets like Venus and Mars, while occultation techniques, where a moon or planet passes in front of a distant star, allow researchers to calculate planetary radii impressive accuracy. The geometric principles remain constant. Light angles and distance combine to reveal scale. A broader scientific context emerges from considering why the sun's rays are nearly parallel at Earth's surface. The vast size of the sun plays a crucial role. With a diameter of about 1,400,000 kilometers, sunlight spreads across space in streams that appear almost uniform over the width of Earth. Instruments aboard missions such as NASA's Parker Solar Probe confirm this near-parallel behavior even as they investigate finer details of the solar wind and magnetic fields. For the purpose of shadow measurements, the approximation works exceptionally well. Historical analyses of Eratosthenes' approach reveal how advanced Hellenistic scientific culture had become. Mathematics, geography, and observational astronomy intersected naturally. Scholars compared reports from distant regions, maintained meticulous travel records, and applied geometric reasoning to practical questions. The measurement of Earth's circumference was not an isolated achievement. It formed part of a growing framework for understanding the world as a coherent physical system. The elegance of the method lies in its accessibility. Two observers need only agree on a date and a local noon measurement. The shadows do the rest. Once the angles have been recorded, the geometry follows naturally. The curvature of Earth ceases to be an abstract claim and becomes a measurable quantity. Even today, at a time when satellite imagery is readily available, the simplicity of the experiment makes it one of the strongest educational tools for illustrating Earth's shape. From a scientific standpoint, the measurement illustrates a larger theme. Simple observations coordinated across distance can reveal global-scale truths. This principle echoes through modern Earth science. Weather stations positioned across continents generate data for climate models. Seismometers distributed globally allow researchers to map the planet's interior. Satellites trace gravity variations that expose the movement of water and ice across regions. Each case mirrors the lesson drawn from two shadow lengths. Distributed information reveals structure. Two sticks separated by a known distance therefore accomplish something profound. They demonstrate that Earth curves beneath one's feet, that sunlight arrives in a predictable geometry, and that the dimensions of the planet can be measured without leaving its surface. A tilted stick with a string and a small weight attached to its end forms one of the simplest instruments ever used to probe the forces acting on a planet's surface. The moment the bob is nudged sideways, a predictable rhythm emerges. The swing repeats itself steady and regular, suggesting a hidden order beneath the motion. That rhythm, once measured with care, reveals the strength of gravity directly. The principle that governs the pendulum's motion has been tested for centuries. Galileo is often credited with recognizing that a pendulum's period, the time required to complete one full back and forth swing, depends primarily on the length of the string rather than the amplitude of the motion. Galileo's insight, made in the late 16th century, set the stage for later refinements by Christian Huygens, who constructed the first pendulum clock in the 17th century. Modern physics confirms these early observations. The period of a simple pendulum increases with the square root of its length and varies inversely with the square root of the local gravitational acceleration. Experiments carried out on Earth demonstrate that local gravity varies subtly from place to place. Mountains, ocean basins, and differences in crustal density all produce small deviations in gravitational strength. These variations are well documented by satellite missions such as NASA's GRACE Gravity Recovery and Climate Experiment and its successor GRACE-FO. Although their instruments operate with extraordinary sensitivity, detecting changes as small as a few microgaules, the underlying concept remains consistent with what a pendulum reveals. Gravity is not uniform across Earth. It reflects the distribution of mass beneath and around the observer. A simple pendulum, however, is adequate for determining the broad value of Earth's surface gravity. Repeated measurements confirm that a 1-meter pendulum completes roughly one swing every 2 seconds at sea level. Shortening the string reduces the period, lengthening it produces slower oscillations. These observations allow a person to calculate the approximate gravitational acceleration of the planet without referencing satellites, lasers, or electronic sensors. The pendulum's dependence on gravity becomes especially clear when considered in extraterrestrial environments. Lunar missions provide an excellent example. Astronauts on the Apollo missions experienced a gravitational field only about 1/6 as strong as Earth's. Footage from the lunar surface clearly shows objects falling more slowly and astronauts bounding more easily. A pendulum brought to the moon would swing far more slowly than its Earth-bound counterpart. The same effect would appear on Mars, where gravity is only about 3/8 of Earth's, a fact confirmed by NASA landers equipped with accelerometers. Knowledge gained from these missions supports a modern understanding of gravitational variation across the solar system. Even small moons and asteroids exhibit measurable gravity. The OSIRIS-REx spacecraft, for instance, detected the faint gravitational tug of asteroid Bennu, allowing mission planners at NASA's Goddard Space Flight Center to adjust the spacecraft's trajectory with remarkable precision. These advanced techniques rely on the very principles a pendulum demonstrates in their simplest form. Returning to the original experiment, the tool remains elegantly minimal. A stick set at an angle, a string, a weight, and a small amount of patience form the entire apparatus. The stick lifts the bob slightly above ground level, ensuring the swing is unobstructed. The string acts as the arm of the pendulum. The weight, or bob, provides inertia. A gentle push initiates the motion. Once the pendulum begins to oscillate, its period can be timed with a modern watch, revealing the character of the gravitational field. The reliability of the measurement depends on the pendulum's ability to swing freely. Friction at the pivot point, the place where the string meets the stick, must be minimal. Air resistance must be small relative to the gravitational force. These requirements are easier to meet than they appear. A smooth string, a modest weight, and a thin support suffice for surprisingly stable oscillation. Huygens' early clocks used similar components to achieve accuracy far superior to previous timekeeping methods. One of the most striking aspects of the pendulum experiment is how much information it provides with so little complexity. Measuring Earth's gravity from scratch illustrates the same principle that drives planetary science today: motion encodes force. Whether studying oscillations, orbital trajectories, or tidal interactions, gravitational effects always reveal themselves through movement. Instruments differ, but the logic remains constant. A personal appreciation for this idea grew during visits to research laboratories where precise gravimeters are used to monitor changes in groundwater ice sheet mass or volcanic activity. Though the devices in those labs rely on lasers and superconducting components, their purpose reflects the pendulum's purpose: quantify how mass interacts with the gravitational field. The difference lies not in the underlying physics, but in the required sensitivity. The original stick and string setup also provides an opportunity to consider gravity's role in everyday experience. Movements that feel natural, walking, balancing, lifting, only function as they do because Earth's gravitational pull remains stable on human scales. A pendulum, by responding predictably, demonstrates that stability, in a visible and measurable way. Even the simple pleasure of observing its steady swing carries an implicit recognition of gravity's constant presence. With the strength of gravity established, another dimension of Earth's behavior becomes accessible. The pendulum reveals gravity's magnitude, but it does not yet confirm that Earth rotates beneath our feet. Detecting rotation requires extending the same principle, letting an object move freely, and observing how its path evolves. A longer cable, a heavier bob, and a more stable support allow the next realization to emerge. The plane of a pendulum swing can appear to rotate, not because the pendulum twists, but because the planet turns underneath it. The key to the demonstration lies in allowing the pendulum to swing for long periods with as little friction as possible. A long cable several meters in length reduces the influence of small disturbances. A heavy bob resists tiny directional shifts. A carefully designed pivot minimizes friction at the point where the cable attaches to its support. With these conditions met, the pendulum can maintain its plane of swing for hours, sometimes for an entire day. Once the pendulum is in motion, a subtle effect slowly becomes visible. The orientation of its path appears to rotate relative to the floor. Jean-Bernard Léon Foucault presented this effect publicly in Paris in 1851. His installation in the Pantheon consisted of a 67-meter cable holding a 28-kilogram brass bob. The pendulum's swing traced a line in sand spread across the floor. Over the course of the day, the line shifted its orientation, sweeping slowly around like the hand of a monumental clock. Foucault's demonstration required no astronomical instruments, no reference to distant stars, and no complex calculations. It relied entirely on free motion and patient observation. The effect arises from a simple principle. Once a pendulum begins to swing, it retains its plane of motion unless an external force alters it. Earth's rotation provides that alteration indirectly. The pendulum does not rotate, the floor beneath it does. From an external, non-rotating reference frame, the pendulum continues its original motion unchanged. From the viewpoint of an observer attached to Earth's surface, however, the pendulum's path seems to drift. Measurements taken at different latitudes reveal that the rate of apparent rotation depends on geographic position. At the North Pole, the pendulum's plane completes a full rotation in roughly 24 hours, matching Earth's rotational period directly. Moving toward the equator slows the apparent rotation. At mid-latitudes, for example, Paris, the pendulum requires more than a day to complete one full apparent revolution. At the equator, the effect disappears entirely. A pendulum release there retains a fixed orientation relative to the Earth's surface because the local direction of rotation does not alter the orientation of the support in a way that affects the swing. These latitude-dependent effects have been confirmed countless times, both in historical installations and in modern educational displays. Science museums around the world maintain Foucault pendulums as permanent exhibits. Their slow drift offers an accessible demonstration of Earth's rotation without relying on astronomical observation or assumptions about celestial geometry. The American Physical Society, along with institutions in Europe and Asia, has documented numerous replications of Foucault's experiment, each consistent with theoretical expectations. An important feature of the pendulum's behavior arises from the concept of inertial frames reference systems in which objects move according to Newton's laws of motion without the influence of fictitious forces. A pendulum suspended from a fixed point in an inertial frame retains its plane of oscillation. Earth, however, rotates continuously, causing the observer's frame to be non-inertial. This mismatch produces the apparent drift. The pendulum is not responding to a mysterious new force. It is faithfully revealing the difference between the motion of the observer and the motion of the pendulum's reference frame. Further clarity comes from considering the direction of the apparent rotation. In the northern hemisphere, the pendulum's plane shifts clockwise when viewed from above. In the southern hemisphere, it shifts counterclockwise. This hemispheric reversal aligns precisely with expectations derived from Earth's rotation direction. The same underlying physics gives rise to atmospheric effects, such as the Coriolis influence on large-scale weather systems deflecting winds and ocean currents. The pendulum captures that influence in its simplest mechanical form. Efforts to improve the precision of Foucault pendulums have produced variations tailored for research purposes. Large installations, some exceeding 20 meters in length, use magnetic or electronic damping to preserve smooth motion while preventing unwanted rotation of the bob around its vertical axis. Observatories and university laboratories sometimes employ pendulum arrays to study subtle changes in local gravitational fields, though these applications require far stricter isolation than public exhibits. Despite such enhancements, the core phenomenon remains accessible with relatively basic equipment. A high ceiling, a long cable, and a sufficiently large mass create a functioning demonstration. The essential requirement is that the pendulums swing freely enough for the Earth's rotation to become detectable over the course of hours. Numerous amateur groups have replicated the experiment in large halls, gymnasiums, and university atriums. Even with modest precision, the drift becomes measurable, reinforcing the idea that the effect belongs not to specialized equipment, but to fundamental physics. Understanding this demonstration also helps illustrate why the experiment cannot be replicated easily with a short household pendulum. Short pendulums complete cycles rapidly and lose energy quickly due to friction and air resistance. Their plane shifts too slowly relative to the rate at which the swing decays. Long pendulums, by contrast, have slower periods and maintain coherence for much longer. The extended duration allows the tiny rotation rate to accumulate into a visible shift. Foucault's original demonstration produced widespread public interest in the mid-19th century. Newspapers, scientific societies, and universities commented on the clarity of the experiment. For many observers, it provided the first internally generated proof of Earth's rotation, one that did not rely on telescopic observations of celestial bodies. Its impact stemmed from the simplicity of its logic. A freely swinging pendulum should keep its plane. The plane moves relative to the ground, therefore the ground must be rotating. This realization fits naturally into the sequence of investigations emerging from the stick in the ground approach. A simple shadow reveals the daily cycle of sunlight. Two shadows reveal the curvature of Earth. A short pendulum reveals gravity's strength. A long pendulum reveals Earth's rotation. Each step builds on direct observation, expanding the scale of inquiry without requiring dramatic changes in equipment. Large stones fixed in deliberate alignment tell a story about ancient attention to the sky. Long before telescopes or written calculations, communities across continents built structures whose geometry reflected consistent observations of the sun, moon, and sometimes bright stars. These places now appear monumental, yet the principles guiding them resemble the same principles demonstrated by a stick in the ground. Stonehenge, perhaps the most widely recognized of these sites, occupies a broad plain in southern England. Archaeological records indicate multiple phases of construction spanning more than 1,000 years, beginning around 3000 BCE. The monument's most distinctive stones, the massive Sarsen trilithons, were raised centuries after the earliest earthworks. Modern surveys conducted by English heritage and researchers from institutions such as University College London reveal careful orientation. Particular stones align with the rising sun on the summer solstice. On that morning, sunlight passes through the monument's central axis, a feature unlikely to have arisen by chance. Civilizations in the Americas developed similar methods. The builders of the Caracol Observatory at Chichen Itza in the Yucatan Peninsula constructed windows and walls that frame the positions of the Sun and Venus at key times of the year. These alignments correspond to seasonal transitions and to the orbital cycle of Venus, which played a significant cultural role in Maya astronomy. Archaeological work supported by the University of Arizona and the Instituto Nacional de Antropología y Historia has documented these directional orientations with precision. Further, South Andean civilizations used pillars and horizon markers to track equinoxes and solstices. The Inca site, known as Intihuatana, often translated as the hitching post of the sun, aligns with the sun's position during the equinox when the midday sun casts the shortest possible shadow. Although popular accounts sometimes dramatize the meaning of these structures, Research published through the American Museum of Natural History emphasizes their practical function as seasonal indicators rather than instruments for esoteric rituals. Africa also contains evidence of early astronomical structures. The Nabta Playa stone circle in southern Egypt predates Stonehenge by several millennia. Studies conducted by the University of Colorado and the National Research Institute of Astronomy and Geophysics in Egypt suggest that some stones mark the direction of the summer solstice sunrise. The site's builders, pastoralists who lived in the region during the early Holocene, likely used the structure to anticipate the arrival of seasonal rains. The persistence of such alignments across cultures suggests convergent reasoning rather than cultural exchange. Communities that depended on environmental cues naturally turned their attention to the sky. By marking horizon positions with durable structures, stones, posts, or carved lines, they developed calendars grounded in empirical observation. These systems required no advanced mathematics. They relied instead on patience, continuity of tradition, and careful attention to natural cycles. Modern interpretations sometimes attribute these achievements to mysterious or extraterrestrial influences. Claims of this kind persist largely because contemporary society often lacks the direct observational experience that guided ancient builders. A structure that aligns with the summer solstice may appear miraculous to an observer who has never tracked the sun's annual drift. Once the underlying cycle is understood, the alignment becomes a predictable outcome of methodical skywatching. Research teams from Cambridge, Oxford, and other universities have emphasized that such constructions fall within the capabilities of ancient engineering. Transporting massive stones while demanding significant labor was feasible with wooden sledges, ropes, and human coordination. Archaeological experiments have shown that groups of fewer than 200 people can move multi-ton stones by rolling them on logs or sliding them across lubricated tracks. These findings align with extensive evidence of social organization in Neolithic and Bronze Age Europe. What distinguishes these sites is not the difficulty of the construction, but the cultural investment in astronomical awareness. Generations of observers recorded solstices, tracked lunar phases, and passed knowledge forward. Their monuments reflect accumulated observations rather than sudden insights. In many cases, ongoing refinements over centuries reveal a dynamic process of calibrating structures to the sky. The conceptual continuity between a prehistoric stone alignment and a modern stick in the ground experiment becomes clearer in this context. Both rely on shadows, horizon points, and repetition. Both convert celestial motion into local markers. Both treat the sky not as a distant abstraction, but as a set of patterns that can be measured and anticipated. The stick captures daily and seasonal cycles on a manageable scale. A monument like Stonehenge captures them on a communal scale, embedding astronomical knowledge into architecture. In visits to solar observatories and archaeological sites, I often find that the most compelling connection between past and present lies not in the structures themselves, but in the underlying method. Long-term observation remains indispensable for scientific inquiry. Missions such as NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter produce continuous records of solar activity. These records serve purposes far beyond cultural timekeeping. They inform models of space weather, plasma dynamics, and magnetic field interactions. Yet the philosophical continuity remains. Repeated observation over long intervals yields deep insight. Ancient observatories demonstrate that a civilization can cultivate an accurate understanding of celestial patterns without formal science. Their achievements remind us that careful watching sustained year after year allows natural cycles to reveal themselves. That fact becomes especially clear when reflecting on how much of today's population lacks familiarity with the sky's slow changes. A person living in a brightly lit urban environment may never notice the sun's seasonal drift or the stars' shifting positions. Artificial light now fills most urban environments, and with it comes a quiet shift in human perception. Patterns that once defined the rhythm of daily life have faded into the background. The gradual movement of sunrise along the horizon, the slow rotation of constellations across seasons, and the subtle variations in midday shadow no longer register for many observers. These changes did not disappear. Visibility simply diminished beneath the brightness of modern life. Light pollution stands at the center of this disconnect. Surveys conducted by NASA in collaboration with the National Park Service show that a significant majority of people in Europe and North America live under skies where the Milky Way is no longer visible. Satellite imagery from the VIRS instrument aboard the Suomi NPP spacecraft maps this glow from orbit, revealing entire regions dominated by persistent artificial brightness. In such environments, only the brightest celestial objects can be seen without specialized equipment. Fainter cues, those needed for tracking sidereal motion or changes in the ecliptic, become inaccessible to the unaided eye. Habitual indoor living reinforces the shift. Temperature control, artificial lighting, and widespread digital media have reduced the amount of time people spend outdoors during dawn and dusk. These are precisely the periods when natural variations in solar position are easiest to detect. Without direct exposure, the sky's changing geometry becomes an abstract idea taught in classrooms rather than a lived experience. A similar trend appears in the perception of nighttime motion, the gradual advancement of constellations across the sky. A pattern that guided ancient travelers is masked by urban lighting and limited sightlines. The 4-minute difference between solar and sidereal days creates a steady shift. Stars rise earlier each night, and over months, different constellations occupy the evening sky. Without consistent visibility, the idea that Earth's rotation dictates stellar motion becomes purely conceptual. Even simple observations such as the changing altitude of Orion over a single-month escape attention, the result is a form of cultural amnesia regarding natural cycles. Ancient communities embedded these cycles into architecture, agriculture, navigation, and ritual. Modern society delegates timekeeping to atomic clock seasons, to digital calendars, and navigation to satellites that communicate with handheld devices. The underlying celestial mechanics remain unchanged. The human relationship to them has shifted. Despite this disconnect, contemporary science relies heavily on the same observational principles that guided early skywatchers. Long-term monitoring continues to play a central role in modern research. For example, the European Space Agency's Gaia mission creates a precise three-dimensional map of the Milky Way by repeatedly measuring the positions and movements of more than 1 billion stars. This effort mirrors the logic of tracking stellar motion over time, though on a scale and with a precision far beyond human vision. Satellites also monitor the sun's changing behavior in continuous detail. The Solar and Heliospheric Observatory SOHO, jointly operated by NASA and ESA, has recorded decades of data on solar cycles, magnetic field variations, and coronal mass ejections. These observations allow researchers to predict space weather and endeavor with direct implications for power grids, satellite operations, and communication networks. The continuity between ancient skywatching and modern solar observation lies in the same basic requirement: repeated attention over extended timescales. Increasing awareness of this continuity may help reestablish a connection between modern life and the celestial patterns that shaped earlier worldviews. Educational programs and observatory outreach events often encourage participants to engage directly with the sky, to identify constellations, track the changing positions of the planets, or measure the length of a midday shadow over months. Even simple demonstrations recreating the analemma or observing the shift of the Big Dipper across seasons can restore awareness of Earth's motion through space. Efforts to reduce light pollution offer another path. Cities in several countries have experimented with shielded streetlights, lower color temperature LEDs, and designated dark sky zones. Studies published by the Journal of Quantitative Spectroscopy and Radiative Transfer show that such measures significantly improve night sky visibility while reducing energy consumption. Improved visibility restores access to natural cycles that once shaped human understanding of the world. A broader point emerges from this exploration. Knowledge of the sky does not require advanced equipment. It requires attention, something ancient builders possessed in abundance. Their stone alignments, calendar systems, and architectural orientations reflect centuries of accumulated observation. Modern society often substitutes precision instruments for that observational continuity. Instruments reveal the same truths, but the experiential connection weakens. Such revelations emerge not from technology, but from consistency. Observers who record the shortest shadow each day develop an awareness of Earth's daily rotation. Those who watch sunrise shift along the horizon recognize the tilt of Earth's axis and the orbit's annual rhythm. Shadow comparisons between distant locations disclose the planet's curvature. Pendulums reveal gravitational strength and, when extended, confirm Earth's rotation. Each step derives from the same root practice, sustained attention to repeated patterns. In many respects, the stick functions as a bridge between intuitive perception and scientific reasoning. Early skywatchers did not begin with formal theory. They began with the recognition that the sun's path changes over time, that shadows follow predictable trends, and that these trends correspond to physical realities. Their conclusions developed gradually informed by generations of observation. Although modern science employs tools of far greater precision satellites, atomic clocks, space-based observatories, the epistemological foundation remains similar. Contemporary missions illustrate this continuity. Instruments aboard the Solar Dynamics Observatory track the sun's movement and surface activity with exquisite accuracy. The GRACE-FO satellites map gravitational variations across the globe, revealing shifts in water mass, ice distribution, and tectonic structure. Gaia charts the positions of stars with a precision unimaginable to ancient astronomers. Despite their sophistication, these missions rely on principles that the stick experiment hints at. Motion reveals forced repetition, uncovers patterns, and consistent measurement builds understanding. An additional insight arises from considering the observational mindset required to extract meaning from a stick's shadow. The process demands patience, repetition, and the ability to compare changes across days, months, and years. In an era characterized by rapid attention cycles, such long-term perception becomes increasingly rare. The sky continues its slow transformations, whether people notice or not, but the ability to interpret those transformations requires a willingness to look carefully. Measurements derived from the stick also help place humanity within a broader cosmic context. Determining the planet's circumference through shadow comparisons, for example, demonstrates that Earth is not infinite or boundless. It is a finite sphere moving through space. Detecting Earth's rotation with a pendulum emphasizes that the ground is never truly still. Observing seasonal changes reveals that Earth's position relative to the sun alters the distribution of sunlight across the surface, shaping climate and ecosystems. Each observation situates human experience within a structured, dynamic environment. The sequence of experiments also reinforces an important methodological lesson. Simple tools can yield profound insights. Many key discoveries in physics and astronomy began with observations that required minimal equipment. Tycho Brahe's naked-eye measurements of planetary motion enabled Johannes Kepler to formulate his laws of planetary orbits. Galileo's early telescopes were crude by modern standards, yet revealed mountains on the moon and moons around Jupiter. Foucault's pendulum needed only a long cable and a heavy bob to demonstrate Earth's rotation. This history demonstrates that scientific understanding emerges not only from advanced technology, but from careful methodology. The stick distills this methodology into its simplest form. It aligns with sunlight casts a shadow and responds to celestial geometry. The patterns generated by those shadows are not subjective impressions. They reflect quantitative relationships that remain valid across centuries and cultures. Reflecting on these relationships also highlights how scientific reasoning achieves universality. Observers in ancient Egypt, Mesoamerica, East Asia, and Europe independently recognized solar and lunar cycles. Their monuments differ in form and purpose, yet their alignments follow the same celestial motions documented today by observatories on Earth and in space. This convergence underscores the idea that the cosmos presents a shared reference frame accessible to anyone willing to observe. Across all these contexts, the most consistent message is that comprehension arises through engagement. Observing the shadow's behavior, comparing sunrise positions, or timing a pendulum swing encourages an active relationship with the natural world. Whether interpreted through the lens of ancient skywatching or modern research, the patterns remain the same. Their significance lies not only in what they reveal about Earth, but also in what they reveal about the process of understanding itself. The sequence of insights gained from the stick leads naturally back to a central idea: the universe is intelligible through observation. No matter how complex the models become or how advanced the instruments grow, the path toward discovery begins with looking outward and paying attention to change. A simple stick placed upright in the ground offers a direct and accessible way to enter that path. Its shadow carries information that connects daily experience to planetary motion and planetary motion to cosmic structure, forming a chain of understanding that remains coherent at every scale. Reflecting on this sequence, I find that the value lies not only in the results, but in the approach itself. The world discloses its structure gradually. Earth's motion, its shape, its gravitational field, and its orientation in space all become visible through motion and change. A person who observes those changes directly begins to understand the planet as a dynamic body rather than a fixed stage. That recognition forms the basis of astronomy, physics, and every science that studies natural systems. Modern instruments now extend this way of seeing across scales unimaginable to early observers mapping solar activity, tracking gravitational variations, measuring stellar positions across billions of kilometers. Yet, the logic behind those missions remains continuous with the observations derived from the stick. Patterns emerge, evidence accumulates, and understanding grows. If you followed this journey from the first shadow to the last swing of the pendulum, I appreciate the time and patience you've given to the process. The measurements we traced together describe not only the behavior of the sky, but also the method by which humans learn about it. Long before telescopes or spacecraft, the universe was accessible to anyone who paused to watch it carefully. Thank you for spending this time with me.